In the prior video, I talked about dealing with phase change and phases. I talked about how the phase is determined by the combination of two things: the kinetic energy of the molecules in that particular phase, or substance, I should say, and the forces of attraction that holds them together. Now, typically, when we talk about those forces of attraction, and that's what I want to focus on at this point, I want to focus your attention on this concept of intermolecular attractions. Now, I want to make sure that I completely make clear to you what that means. Inter means between molecules. So if we have two water molecules, I have here, these are, water. And what I'm referring to is the force of attraction between the two molecules. I am not talking about bonds, the bonds that hold two atoms together. We would call that intramolecular, not intermolecular. So we aren't talking about bonds. We are talking about the forces of attraction that hold two molecules together, one to the other, or two or more, I should say. And these are, and I mentioned this earlier in the other video, but these are directly related to these positive and negative charges interacting. So we're dealing with positive and negative charges interacting. I didn't mean to cross those out. Okay, so typically we're saying positive charges are attracted to negative charges. And actually, even though we're talking of forces of attraction, there can be repulsive forces when two negative things are interacting or two positive things are interacting. So both of those come into play to help us understand how molecules are connected to one another. The easy case is when we deal with ions. We take the positive ion is attracted to the negative ion. We see that in ionic solids. Sodium ions are attracted to chloride ions. But then, in a more subtle way, and I mentioned this before, is when we have polar molecules, they have a negative end and a positive end. Now, that doesn't mean that they have a formal charge. This is where we get into the idea of a partial charge. Partial charges, usually you'll see them written with the delta. So one end will have the partial positive charge, and the other end will have a partial negative charge. And then those ends will align so that the partial positive charge is interacting with the partial negative charge. So if we look at water, I just erased all that stuff. You might want to redraw, if you're taking notes, you might want to redraw water. Anyway, the point is, this red, I think I mentioned before, is oxygen, and the white is hydrogen. Well, oxygen has a higher electronegativity than the hydrogen, and so the dipole for this bond is going to go in that direction, and the dipole for that bond is going to go in that direction. We represent dipoles by these funky looking arrows, where we have the arrow pointing in the direction from positive to negative. The arrowhead designates the negative part, where there's a partial negative, and the positive end, of course, is where you have the partial positive. So what we're showing here is that the dipoles then of water, in fact we have a net dipole for water, that, as you may recall from the thing I reminded you about for Chem 112, is you add these two dipoles together and you get a net dipole. Well, these things align so that the partial positive charges of water are in being attracted to the partial negative charge of water. So that's kind of what we're talking about. We will mention this and get into this in greater detail, but hydrogen bonding is a special type of intermolecular force. Even though we use the word bonding, it's technically not a bond. It's still an intermolecular force of attraction. And we'll learn about how even nonpolar molecules can interact with each other. Now, there's something called Coulomb's law. You have actually been introduced to it earlier in General Chemistry 1, Chem 111 at Boise State. And Coulomb's law helps us understand these relationships that you see here. So I have Coulomb's law right here. So the force of the attraction between the two species, the positive and negative, is directly proportional to the magnitude of the charges. That's what Q is. So like, let's say this is +2 and that's -1. That kind of tells you the magnitude of those charges. R here is, that's the distance. And K is just a constant. We're not going to do any calculations with this, so I'm just going to tell you. It's a constant. And so it's a proportionality constant. So the bigger the charges, the bigger the force of attraction. The closer, so the distance, as the distances get closer, force of attraction gets bigger because they're inversely proportional. So force is directly proportional with the charges, and force of attraction is inversely proportional with the distance. So if you pull them apart, the attraction is weaker. Okay, whoops, I'll move this out of the way. Hold on. Now it's important to note that when we are comparing intermolecular forces of attraction with the intramolecular, so again, that's the actual bonds, these are much stronger than the intermolecular force of attraction. So the intra is much stronger than the inter. So if we're like comparing bonding forces between atoms versus the attractive forces are pretty small compared to a covalent bond that's holding things together. Now I'm gonna just kind of quick overview. We're going to learn about some different forces of attraction. We have dispersion forces, dipole-dipole attractions, and hydrogen bonds. And then we'll also see one more later called a dipole ion or ion-dipole interaction. It turns out these are the weakest. Then comes dipole-dipole, so that's kind of mid. Then comes hydrogen bonds, and ion-dipole are the strongest of these. Okay, so let's look at these in a little more depth. Let's talk about dispersion forces. Dispersion forces are forces between two molecules that involve the formation of a temporary dipole. And it turns out that even polar molecules that have a permanent dipole can also have temporary dipoles as well. So let's talk about what that even means. I'm going to draw your attention down here first to these little molecules that we have drawn here. Here's some molecules. And within a molecule, we're aware that electrons are moving around within the atom, within the electron cloud. So these things are buzzing around, okay? At any given time, you might find that the electrons may be distributed in an uneven way so that more show up on one side than the other. So if we're using just the 2 electrons here in this helium molecule, here we're showing, here's a helium where there's a electron here and here, there's electron here and here, so they're on either side, there's electron on both sides of the atom. But periodically, every now and then, the electrons will be found more on one side than the other side. And when that happens, that sets up what we know as an instantaneous dipole. And I'll write it down here. Also referred to as a temporary dipole. I like instantaneous because at any given moment, there could be a dipole. These electrons are buzzing all over the place. Another way to sort of draw this is to think of a nonpolar molecule as having a fairly even, so if this is nonpolar molecule, there is no permanent dipole, so the electrons are buzzing around, and maybe in one moment you'll check the electrons and they kind of are distributed on one side of the molecule. That would be the case that we're showing here down at the bottom in frame 3. Okay, and then another time, maybe you'll check it, and it's like that. And so it's a moving target in all 3 directions, X, Y, and Z. So coming out of the page, going into the page, and if you were to sum these up and average them, you would find this, because there would be randomly distributed at any given time. Okay, so these instantaneous dipoles, every molecule, even nonpolar molecules, have. Polar molecules can have it too. It's just these would happen on top of an already permanent dipole. Okay, so what happens then is as these instantaneous dipoles happen, and you have another molecule. Let's say I have another molecule. I'll use this example down here. Let's say you have another helium, okay, and that helium's here, and now you have another molecule where the electrons are also on one side, okay, just like we have here. So here's your nucleus. These are your electrons, okay. Then you're going to have these partial dipoles, partial poles again, partial charges, I should say. And so this negative end of this molecule, if it happens to be close to another, I say molecule, or in this case these are heliums, because you can see there's 2 protons and 2 neutrons, 2 electrons, that makes it helium. Helium is not polar by itself, and so you bring this helium atom close to another one, and what's going to happen is that these instantaneous dipoles are going to align so that you have a negative dipole. The negative end of this instantaneous dipole is going to line up with the positive end, and so they'll be attracted. And if you really think about it, if you were to bring 2 molecules close together, 2 heliums close together, let's say we brought these 2 close together, okay? Let's just say, let's pretend these are just 2 molecules, 2 hydrogen, let's say it again, 2 helium atoms, okay? And you bring them close together, the electrons are going to repel each other, right? Negative charges will also repel each other. And essentially what's going to happen is if this electron bumps over here, then these electrons are going to go over there. And they're going to induce a dipole with one another. One is going to cause the other to have an induced dipole. That's what this is referring to here. A temporary dipole is established in one molecule. This temporary dipole is established in one molecule, and when it's next to another, it can induce a dipole in all the other molecules. they're not going to necessarily stay this way. As like, let's say these two molecules are here. It's just that if these electrons move over here, guess what's going to happen? Those will go over there, and they'll still be attracted to each other because they're inducing dipoles into each other. The electrons repel each other, and that causes the establishment of two dipoles. One can cause the dipole in the other. That's why we call that induced dipole. And sometimes dispersion forces, and especially in my case, because that's how I think about them, dispersion forces can be thought of as an induced dipole. So induced dipole interaction. So that's one possibility. So you have two nonpolar molecules inducing dipoles in each other. So we can call that an induced dipole interaction. All right. Now, you can also have other types of induced dipoles. So I want you to be aware of this. So we have induced dipole. Now imagine a situation, and so we'll look at this. Imagine a situation where now you have, let's say you have a dipole. So I'm gonna just write some molecule like this, and we're just gonna, it's permanently looking like this. So we're gonna have a positive side and a negative side. And now you bring in some molecule that's nonpolar. Okay, so this is a polar molecule, has a permanent dipole, and once it gets close to a nonpolar molecule, this dipole is going to repel the electrons to the other side and cause it to form a dipole that it can interact with. So in this case, this would be a molecule that's a polar molecule. It has a dipole, permanent dipole, and if this is a nonpolar molecule, this would be an induced dipole. Whoops, I hit the wrong button here. So this would be an induced dipole. So we would say when a dipole, like let's say water interacts, so water is polar, and water can interact with oxygen. And by the way, oxygen is nonpolar. Yet oxygen gets dissolved in water. Fish are happy about that, because they can breathe. And so that oxygen then comes into contact with the dipole of water, and water, the oxygen has an induced dipole. So the strongest part to the interaction that water can do, because it's polar, is a dipole. The strongest thing that a nonpolar thing can donate to the interaction is an induced dipole. So we would call this kind of interaction that I'm describing a dipole-induced dipole interaction. So that's another type of dispersion force. My preference is that when you see stuff like this, that you don't just label it as London forces, or because that's another name for it, or dispersion forces, but instead I would prefer you to indicate to me that you recognize if it's two nonpolar things that you would have induced dipole, and if it's a polar interaction with a nonpolar molecule, that we would call that dipole, induced dipole. So all dispersion forces involve interactions with induced dipoles. So that's something you'll have to think about. Now the truth is I just sketched a lot of this stuff, but this is more or less talking about what I'm trying to describe in my little drawing. This is where you'll get the alignment of a bunch of induced dipoles so that the partial positive charges interact with the partial negative charges. And this is what would happen if you put a bunch of helium molecules together, such as if you had liquid helium in a tank or something like that. So here's where we want to think a little bit again about Coulomb's law. Remember, Coulomb's law is the force of attraction is equal to some constant K times the charge on one thing times the charge on the other thing that's interacting with times the divided by the distance squared. And so you can increase the force of the attraction if your charges are bigger. So let's think about how you can compare different, say, non-polar molecules that have different induced dipoles and determine which ones would have the bigger force of attraction. Well, as I mentioned before, I'm going to move up here again. We are talking about how induced dipoles are formed when electrons can move to one side of the molecule and leave the other side deficient. So then we set up this partial negative, partial positive. Now, if the electrons are held closely together to the nucleus, they're not as easily distorted. They don't move to one side more readily than the other. But if those electrons are not as tightly held by the nucleus, then they're more able to redistribute. That whole concept of being able to redistribute the electrons is called polarizability. So if we can think about what can contribute to the polarizability of electrons, molecules and atoms that have more polarizable electrons will be able to have stronger differences in partial charge, which will set up bigger induced dipoles, heavier magnitude. And then if we go back, I shouldn't say heavier, greater magnitude. Then if we go back to this, that means we make these bigger. This difference is going to be bigger, and that can lead to a stronger force of attraction. So polarizability, then, you have to think about what is it that can kind of loosen up those electrons in an atom. Well, in Chem 111, General Chem 1, you learned about things like effective nuclear charge and all of those kinds of forces of interaction between a nucleus and an electron that can hold that electron in the molecule. And we learned that as you add more electrons, those electrons become, they don't see the nucleus with the same way. In fact, the effective nuclear charge that's holding those electrons gets weaker. And if you can add more electrons, make the electrons more weakly held, you can actually lead to polarizability, and you can get a stronger induced dipole in that process. So things like, if it has a larger molar mass, it's going to have more electrons. If it has more electrons, it's going to have a larger electron cloud. If it has a larger electron cloud, it has increased polarizability and stronger interactions. Okay? And then this other thing, shape of the molecule, this becomes important as we apply some of those things we learned in the organic chemistry section. When you have, say, there's a 1, 2, 3, 4, 5 carbon pentane. That's what I just drew here is pentane. And I compare that to something that looks similar. I can draw something like this. Now we have a branch chain. Okay. So now I have 1, 2, 3, 4, 5, but now I have a branch. This is linear. This is branched. So then we can kind of say something about the shape. So if we have a longer molecule with less branches, there'll be more surface-to-surface contact. So more of these will see each other than in this case, because the branches kind of cause not as nice of stacking of the molecules. So if you had another molecule like that, it could lay out and have more surface-to-surface contact. So in general, when they have more surface-to-surface contact, they're going to have more induced dipoles to interact with each other. So if I make these chains longer, I can increase the length of these chains if I keep them linear. This is called a linear chain, even though it's zigzag, but that's how carbon, the geometry is of carbon, look like that. Anyway, the point is, these things, as they go longer, not only do we increase the molar mass and how many electrons, but we also can increase the surface area that they can interact with. The way I like to think about this is if you look at, if you try to tie someone to a chair. I know that sounds like a terrible, terrible thing to say, but let's say we have a chair. That's my chair, and there's somebody in it. Okay. Ah, boy, I'm not an artist. Okay, so we got someone in a chair, and I put one thread around them. They probably could break free of that thread. But if I were to take that thread and keep wrapping around and increase the amount of interactions of thread, loops of thread around that person, I can hold them in that chair just as if I was chaining them somehow. So that's kind of what this is about. If there's more points to interact with, even if they're weak interactions, you can actually cause pretty great forces of attraction by just including a lot more atoms. It's kind of the idea here. So the number of atoms, the number of electrons, and how they're arranged will influence how strong these forces of attractions are. Okay? Now, truthfully, I just want you to know I'm not going to spend a whole lot of time on this, but this is just another way to show. I think I put the same thing twice, by the way. I just realized that. I'm sorry about that. Oops, I meant to cross that out. Just focus on that. But this is just showing that interaction, okay? Remember, now I just want to remind you something. We'll talk more about boiling in a minute, but boiling is a phase change when you go from a liquid to a gas. And so in order to cause a liquid to boil, you have to add enough kinetic energy to break free for the atoms or molecules to break free from one another in those intermolecular forces of attraction so that they can be released into the gas phase. And so we can use boiling point because that is the temperature at which boiling occurs. We can see that as you increase in mass for the noble gases, you're seeing an increase in boiling point. So as you add more electrons, the forces that are holding the molecules together are getting bigger. And since they're getting bigger, they're stronger, it takes more kinetic energy to break free. And you can see that the boiling points show that because it takes more and more energy to cause the liquid forms of these noble gases to turn into a solid. I'm sorry, a gas. Okay? And this is, again, I did my little sketches, but this is just showing the same thing I mentioned before. Here's, you got a branch chain molecule, and you have pentane. I even used pentane. So here's another type of pentane. It's got 5 carbons. This has 5 carbons, so they're isomers. This one has 3, so this one has 12 hydrogens, and this one has also 12 hydrogens, so they're isomers, C5H12. But this one has more surface area for these things to interact in these. So this one, this shape, is actually going to have a higher force of attraction holding these together. And if you go ahead and compare that to this one, there's just a very small point where these things can interact. So if we were going to compare these boiling points, this would have a bigger boiling point because it would take more energy to break these interactions apart than it would for this one. We can also look at the chain length of different alkanes. When we say N-alkane, that's a way of just saying it's just alkane, as you remember, it means that you have all these single bonds, and N is just letting you know that these are straight chains. So we got pentane, hexane, heptane, octane, nonane. So as we go up in molecular weight, so does the boiling point. We have more atoms and more area where they can interact. So in this case, there's actually two reasons why these boiling points are going up. One, molar mass, and since these are straight chains, there's more surface area to interact with. And in order to beat you over the head with stuff, some general thoughts, and you can explain this now because of the stuff we just said about shape, for instance. Branch chains tend to have lower boiling points than straight chains with the same molar masses, and that's because they have more surface-to-surface contact for the straight chain, so there's more interactions, and those things take more energy to break them apart than the branch chains. So the branch chains have lower boiling points. Okay, so I kind of went over in dispersion forces and the idea of induced dipole interactions. And those dispersion forces are the weakest kind of intermolecular forces. But now let's go to the next level. The next strongest type of attraction are when you have two polar molecules, each having a dipole. We can have a dipole-dipole attraction. So pretty much these involve things that have permanent dipoles. And remember bond polarity and shape. Do they have a net dipole moment? I'll come back to that in a second. Do they have a net dipole moment? If you can answer yes to all of those things, then you know that they're polar molecules and they have a permanent dipole. That means that they have a permanent partial positive and a permanent partial negative. And as I mentioned before, though, and just to say, even these can still have further induced dipoles. I'll try to draw a picture to demonstrate what I mean by that. So let's say we have, let's just say here's a molecule that has a partial positive charge and a partial negative charge, and it's, let's say it's got a permanent dipole. All right, the electrons can still slosh around, and they might move a little bit over there, so then you can have a bit of an induced dipole as well. But then since they're moving around, it can go back again, or they can redistribute. What's always going to be is this permanent dipole, but even on top of that, in a much more subtle way, and they do not contribute as much, even polar molecules can still have induced dipoles because the electrons are bouncing around all over the place. So, as it turns out, molecules that are polar, that have those permanent dipoles, they interact with one another through these dipole-dipole interactions, and they tend to be stronger, so they tend to have higher boiling points and higher melting points. Now, if you have a long carbon chain where it's all induced dipole, but it's a really long chain with lots of interactions, sometimes those boiling points can be higher. But if you compare the same molecular weight, say, of a nonpolar to a polar, and they both have the same molecular weight or really close, the nonpolar thing is going to have a lower boiling point and a lower melting point than the polar molecule with the same number of atoms. And what this is just showing you, I like using lots of pictures, and so I don't have a ton to say about this, other than you can see you got different polar molecules, and in this case we have, this is some kind of acetone, it's called, so it's looks like a acetone, which has a ketone in it and stuff like that. This should be a, sorry, let me I'm noticing this should be like that. That should be showing a double bond. I just noticed. But when the electrostatic potential map makes it so that the red, this talks about charges, the red is going to have negative and the blue is going to have positive. So the blue part is positive, the red part is negative, and so you can kind of see it as a net dipole. And so it has partial permanent dipoles, and so they align themselves so that the negatives match with the positives. It's as that simple. If you have a permanent dipole, the charges are going to align so that the negatives go with the positives. This is the general concept here for these forces of attraction. Negatives go with positives, and two positives repel and two negatives repel. If you can keep that straight, and then you can figure out which end of a molecule has a partial negative charge because it's got more electronegativity in that direction, it'll have more electrons on that side, then you'll always be able to figure out how they're going to interact. So we got formaldehyde here. Formaldehyde, just as a reminder, that's a ketone, but this whole molecule is an aldehyde. And you can compare, these are really close in molar mass. There's small difference. That small difference is not enough to make a big difference when it comes to things like the force of attraction. Like if these induced dipoles, these are not going to be terribly different. Not enough to explain the difference in melting points and boiling points. Here's ethane. Ethane is a gas, and so is formaldehyde when it's in its pure form is also a gas. But if we look at them in their liquid forms, liquid formaldehyde has a boiling point of minus 19.5 and a melting point of minus 92. But compare those to these. This is much lower. This is much lower. And even though they have similar molar masses, so they shouldn't have that difference if it was just purely through dispersion forces like induced dipole, because this one has a dipole, because the CO is going to give it a dipole, okay, then because this is a polar molecule, the forces of attraction are going to be greater. It's going to take higher temperatures to cause the phases to change. Now, there is a special type of dipole-dipole interaction called a hydrogen bond. So a hydrogen bond is a special type of dipole-dipole interaction. So this isn't just any old dipole-dipole. This is a dipole that is formed by either an OH, NH, FH, and it also could be a CO, is another type of dipole. C double bond O. I'll mention this. So if you have this is kind of some notes that came specifically with our book, and I don't mind using them, but I'm going to add to this just a little bit. I'm going to say it this way. If you have a polar covalent bond, okay, polar covalent bond with F, O, or N, fluorine, oxygen, or nitrogen, that means that these F, O, or N polar covalent bonds, so this is a polar covalent bond, all of these are polar covalent bonds, and they involve F, O, or N, okay? Then a hydrogen bond can form. Now the molecule, polar covalent bond, but they also have to be a polar molecule. So if you have a polar molecule a polar molecule that has a polar covalent bond with FO or N, then that FO or N can hydrogen bond with a hydrogen that is connected to an F, O, or N. What? You may be saying, but I'll tell you. So what I'm saying is that if you have a hydrogen that is connected to a F, O, or N, and that hydrogen can interact with a F, O, or N that's somehow involved in a covalent bond, a polar covalent bond in a polar molecule, they can hydrogen bond. Okay? If that hydrogen is attached to a carbon or something else, so I'm going to show you a few things. So let's say I have this molecule here. Okay? That molecule cannot hydrogen bond at all. 1, nonpolar. 2, this hydrogen is not attached to a FO or N. So that makes this incapable of hydrogen bonding, and it's also nonpolar, so it really can't have a dipole-dipole interaction either. Okay? Water, on the other hand. Okay? I'll draw the Lewis dot of water. Water has an oxygen that is part of a polar covalent bond in a polar molecule, and it also have hydrogens that are attached to an oxygen, so that's F or N. Water can hydrogen bond. Okay, so that now there's hydrogen bonding. Now we call it bonding, hydrogen bonding, not because it's an actual bond. It's still an intermolecular force of attraction. It's a very strong dipole-dipole interaction. Hydrogen bonds are when we aren't dealing with when we're dealing with dipoles, okay? Hydrogen bonds are the strongest. There is something else that's stronger, and that would be an ion-dipole interaction, because the ion has a formal positive charge or negative charge. And then there's also ionic interactions, negatives and positive, formal negative charge, formal positive. Those will be stronger yet. So you have to kind of compare all those things. But when it comes to molecules not having any formal charges, hydrogen bonds are the strongest type of intermolecular force. Okay? So this is showing some of those things here. We have a bunch of, here's HO, HO, HO. Oh wait, this is HCl. So this is HCl, HCl, HCl. And so it's showing that they can hydrogen bond. HCl, sorry. I am so sorry. HF, sorry. So if this is hydrofluoric acid, HF, okay? That HF can hydrogen bond because the H is connected to an F, so that fills this. And the F, the fluorine, is part of a polar covalent bond in a polar molecule. So we can get hydrogen bonding then here. That's what we're trying to demonstrate. I said HCl. I don't know why I did that, because I knew it was HF, but out came HCl, so I'm sorry if that confused you. So I mentioned water can hydrogen bond with itself. So here's hydrogen bonding, and we often represent hydrogen bonding with these little dots. Do not draw a straight line, because that's telling me that a covalent bond, and that's not the same. Hydrogen bond is still negative charges interacting with positive charges. And then ethanol, well, that's an alcohol. So I'll draw ethanol. Here's ethanol. Okay? So it's got one carbon here, another carbon here, because this is another, these are ways of drawing. Here, I'll draw in the carbons to make it a little easier. I'll show you what I mean. So I have a carbon and a hydrogen, hydrogen here, and then I have H, H, H. So this is ethyl alcohol. This is the active ingredient in tequila. And so if you take the alcohols, they actually have the, I'll draw this little Lewis dot sort of, it's not a perfect Lewis dot, but I'll draw the electrons here. So you can see that, honestly, there's a dipole in this direction. There's a dipole. That's showing the same thing there. And those things can hydrogen bond. So the hydrogen of one of the alcohol can hydrogen bond with the oxygen of the other alcohol. And if you happen to have alcohol mixed with water, the water can interact with the alcohol. So you could have a situation like this. So I have my water interacting with the hydrogen from the alcohol. And I'm just going to draw it this way. So you can see the negative part of the dipole of the water can interact with the positive part of the dipole of the alcohol. And since this is a hydrogen that's connected to an oxygen, it's capable of hydrogen bonding. And since this oxygen is part of a polar covalent bond, it can also hydrogen bond. And so therefore, the strongest force of attraction that can take place between alcohol and water is indeed the hydrogen bond. So that interaction is strongest. Now, this part of, and here's something to keep in mind, that sometimes if you have a molecule like a bigger molecule, you can have part of that molecule be polar and the other part be nonpolar. So this part, the nonpolar part, would be able to interact through induced dipoles and dispersion forces, whereas the alcohol is polar. Its strongest force of attraction would be through hydrogen bonding. Okay? And so if we look at this, hydrogen bonds are then stronger than other dipole-dipole interactions and stronger than dispersion forces, especially if you're combining the same amount of molecules. If you're comparing the interactions between, say, a nonpolar molecule and a polar and a hydrogen bonding molecule with the same number of atoms, the hydrogen bonder is always going to have stronger force of attraction holding it together. Now here's a really good couple of charts that help look at the influence of a hydrogen bonder. Okay, first of all, I want you to look at these molecules here. Okay, they are isomers. Ethyl alcohol, dimethyl ether. Same number of everything. Same molar mass. Dimethyl ether has a boiling point of -22 and a melting point of -138. Compare that to ethanol. Ethanol 78.3 and 114.1. This molecule is capable of forming a dipole. This molecule is capable of forming a dipole, and it can hydrogen bond. And the hydrogen bonding, this forms a dipole-dipole interaction. Very weak one, it turns out. So this one can do a dipole-dipole interaction. This one H bonds. And to show you how much stronger a hydrogen bond is than a typical dipole-dipole, doing this comparison, boiling point is about 100 degrees greater. 100 degrees greater. That means it takes that much more energy to break the liquid apart into the gas phase than it does for a very similar isomer. And the big difference is hydrogen bonding can take place. Now you might be saying, wait a minute, there's hydrogens here and oxygens here. How come that can't hydrogen bond? Well, I'll draw it out. This is what this is showing. So we have, our water, and we have the capability of this ether then, dimethyl ether. That's what it looks like. There is a weak dipole in this direction. Part of the weakness has to do with the angle here is pretty wide because of these take up space and push away from each other. So that's why it's a little weaker. In fact, in organic chemistry, when you learn, if you go on to organic chemistry as a course, you're going to learn that dimethyl ether, and diethyl ether, they're similar, behave much more like nonpolar molecules than polar. That's how weak the dipole-dipole interaction is. Anyway, point is, you might be saying, why can't that hydrogen bond with itself? Well, yes, you do have a polar covalent bond with a polar molecule. That oxygen is part of that, but these are the wrong kind of hydrogens. Remember, the hydrogen has to be connected to F or N, and these hydrogens are not. They are connected to carbon. Incapable of hydrogen bonding. So this molecule, the best it can do is dipole-dipole and some dispersion forces. This can do hydrogen bonds and dispersion forces, and those hydrogen bonds, by golly, make a huge difference in the behavior. And we can see a very similar trend if we look down here and we look at the trend here. We have, if we look at group 4A, okay, and we see we have H2TE, H2, this is selenium, sulfur, H2S, and we're noticing that as the molar mass goes down, the boiling point does too. These are largely being interacting through dispersion forces, induced dipole, and therefore the heavier, the bigger molecular weight molecules have stronger forces of attraction. That's why they take more energy to break them apart. But look at when you do H2O. The hydrogen bonding just blows up the boiling point. It takes way more energy. So even though this is the lightest molecule compared to these, it has hydrogen bonding, and that overwhelms everything. Hydrogen bonding wins. If you do a similar kind of thing with this, there's no hydrogen bonding. It's all intermolecular forces dealing with nonpolar molecules, and those nonpolar molecules all have induced dipole, really weak. So the trend is, as the molar mass goes down, so does the boiling point. And that's exactly what you'd think. But when you throw in something like hydrogen bonding, like water, that messes everything up. Really huge difference maker, hydrogen bonding does. Finally, we're looking at ion-dipole interactions. That would be like salt water. You dissolve some sodium chloride in salt. That's what this is describing. And I like the picture. That way I don't have to draw it. But what's happening is the dipoles are lining up with the ions so that you can maximize the favorable interactions. So the positive ends of the water molecules, that's your dipoles, are lining up with the negative anion. So when you dissolve, that's what's happening. And then the negative ends of the dipoles of water are lining up with the positive ion. So even though we have an ion-dipole interaction, you're still having negatives matching with positives and vice versa. And then what happens is, because you have this sphere of water that forms around both of these, we call that a sphere of, because it's water, we call it the sphere of hydration. If we switch the solvent, we'd say it's a sphere of solvation. So because it's water, it's called the sphere of hydration. If it was something else, some other solvent besides water that has a or whatever, if you form this, we would call that a sphere of solvation. But with water, we call it sphere of hydration. And so here's kind of what happens. I'll just kind of give you a sense. So let's say we have our sodium ion, and then we got some waters, right? They start interacting the right way with here, and so they surround this. And then in all three directions, then these waters, they also align. They're hydrogen bonding with the first inner sphere of water, plus they are feeling some of this charge. So they're going to align and they grow out in all X, Y, and Z directions. So into the page, out of the page, in both, all the way around, and you form a sphere of hydration. That's what we call that. So if we kind of look at this, we got dispersion forces, induced dipole. So these are induced dipole. Anything, dispersion forces are anything that involves an induced dipole interaction, okay? They're present in all molecules and atoms, and the magnitude, how big those dispersion forces are, depends on how many electrons there are. The more polarizable they are, the stronger the force of attraction. Polar molecules, also on top of the dispersion, they also have dipole interactions, which are stronger than dispersion forces. And then continuing with the summary, hydrogen bonds are the strongest intermolecular force outside of an ion dipole, which is stronger than a hydrogen bond. And hydrogen bonds are a special type of dipole-dipole interaction, where you have a hydrogen that's attached to a O, N, or F, combining with an O, N, or F that's part of a polar covalent bond. That's what makes a hydrogen bond, and that's all. I shouldn't say, I'm going to, at this point, introduce one thought that we won't worry about here in Chem 112, but I'm going to mention it to you because there are examples in biochemistry, my field, where sometimes we see hydrogen bonding where we think about SH. But for the purposes of Chem 112, we will not consider that. But I'm going to mention it so that when you hear it in biochem, and especially if you take me for biochem, you're not going to be like, well, that son of a gun, he lied to me. No, I'm just warning you ahead of time. But for sort of more traditional way of treating this, we'll think of hydrogen bonds as I earlier defined. Keeping in mind, down the road, we might add one more possibility when we deal with biochem, okay? And then I talked about ion dipoles. So you can take a look at those in this little table here. Kind of summarizes it nice, and it kind of shows you the hierarchy. You have dispersion forces, dipole-dipole, hydrogen bonding, and ion dipole. And the strength increases as you look down, okay? That's the end of this part.